Welcome back, everyone. So, am I audible, sir?
Yeah, I can hear you.
Okay, thank you.
Right.
So, right now we have the second keynote speech by Dr. Waleingne Salidev. It gives me immense pleasure to introduce Dr. Waleingne. He is currently serving as a research faculty and research scientist at Shandong University of Science and Technology, Qingdao, China. He completed his PhD in mechanical engineering from University Technology Petronas, Malaysia, where his research focused on fault diagnostics, condition monitoring, and performance evaluation of industrial gas turbines. Prior to his current position, he worked as a research scientist at University Technology Petronas and also served as a lecturer at Addis Ababa Science and Technology University, Ethiopia, where he taught several courses like thermodynamics, heat transfer, mechatronics, strength of materials, machinery design, finite element method, etc., while supervising various undergraduate research projects. His research interests include gas turbine systems, artificial intelligence, machine learning, predictive maintenance, fault diagnostics, condition monitoring, and energy systems. He has authored numerous high quality publications in internationally reputed journals with significant contributions in the application of AI and machine learning for industrial gas turbine diagnostics and performance optimization. In recognition of his outstanding research contributions, Dr. Salili received the prestigious 2025 ASME Turbo Expo Early Career Engineer Award from the American Society of Mechanical Engineers, along with several other international scholarships and research awards. Today, we are privileged to have him with us to share his expertise and insights. I am confident that his presentation will both informative and inspiring. Thank you, sir, for gracing this event. Uh, Kindly continue with your talk. Thank you, sir.
Thank you very much for the very wonderful introduction. Uh, I really appreciate that. Let me share my screen from my side and um, okay. Show my screen. Can you see my screen now? Is it displayed?
Yes, sir. We can see your
Okay.
screen.
Okay. Thank you. Thank you very much. Okay. My presentation title is Gas Turbine Condition Monitoring Trends and Approaches. I will begin my presentation by introducing the concept of maintenance to just have a common background. Maintenance can be defined as the action taken to protect the system or components from failing by just repairing or replacing its broken parts to offset the performance deteriorated because of some physical faults in the system. So the main goal is to minimize downtime, to increase the component or the machine life, to reduce operation and maintenance costs, and to minimize fuel consumption and emission, and to improve the reliability, availability, and performance, and by reducing costs.
Excuse me, doctor. Excuse me,
Yeah.
doctor. Your screen is not visible.
My screen is not visible.
Yes, only your static screen is visible. No? We cannot see your slides. Can you please
Ah,
check?
okay. Let me check again. Hmm. And now, is my screen visible on the other side?
No, we can't see your slideshow. Slides are not visible.
Okay. Still no?
Yes, it is visible now.
Yeah, oh, it's visible now. Oh, okay. Thank you for confirming. Okay. So shall I proceed?
Yes, sir. It is
All right.
visible. You can proceed.
Okay. Perfect. Thank you. Maybe recap the first slide as well. So the title of my presentation is gas turbine condition monitoring trends and approaches. So to just have a common background about maintenance, let me just give some introduction about it. It's an action taken to protect a system or component from failing by repairing or replacing its broken part to offset the deteriorated performance. So the idea of taking maintenance is to minimize downtime, to increase component or machine life, to reduce operation and maintenance cost by improving the performance of the system. So we basically now, traditionally we have three types of maintenance approaches: corrective maintenance, preventive maintenance, and predictive maintenance. The first one is the corrective one, which is the run to failure approach. Is also known as breakdown or reactive maintenance. It involves fixing or changing broken components. It has high downtime and high operation and maintenance cost. And the second type is preventive maintenance. Uh, this one called schedule type maintenance has obviously benefit over reactive maintenance, but it causes excessive replacement of parts that may still be in good working condition. So sometimes because of the schedule, we may remove the components that might be still functional. And the third type is predictive maintenance, which is the most promising in the fancy one, better than corrective and preventive maintenance. It depends on the actual condition of the system. By monitoring the performance of the system, the maintenance will be conducted. So relatively low operation and maintenance cost, low downtime, improved reliability, availability, performance, and potential failure condition are identified easily enough. It has a benefit of cost saving over preventive and corrective maintenance types. So when we summarize, when we do comparison and summarize these three types of maintenance, the preventive, predictive, and corrective maintenance, we can see from the figures that the preventive maintenance has a low performance cost, but high maintenance cost. And corrective maintenance has low maintenance cost, but high performance cost. The predictive one, the optimized one, as you can see, it has better performance. The cost, the total cost is minimized from the others. So in this presentation, we focused on the third approach, the condition monitoring approach, which is the predictive maintenance type. So, the idea behind condition monitoring is monitoring the performance of the system. And the maintenance action will be taken by by the actual, depending on the actual performance of the system. And it relies on the deviation of measured parameters such as temperature, pressure, shaft speed, and other parameters, station parameters in the system. So I used the gas turbine as a case engine. I mean, for this presentation, in gas turbine we have several physical faults. Fouling is the most common one, like erosion, corrosion, foreign object damage, and tip clearance. So fouling is the accumulation of sands, dust, ash, oil droplets, water mists, hydrocarbons, and industrial chemicals. When this thing happen in the gas turbine, the flow rate, specifically if it happens in the compressor part, the flow rate of the air will be disrupted or reduced, and the efficiency as well will be reduced. So it affects increased surface roughness, influence flow dynamics, decrease in air mass flow rate in gas turbine, decrease in heat transfer effectiveness in heat exchanger. So as you can see from the picture here, the compressor fouling, transformer fouling, and heat exchanger fouling. So generally, fouling is responsible for 70 to 85% of the performance deterioration of the gas turbine. So the most common fault in gas turbine is fouling. But the good part is it can be recovered. I mean, the performance decline can be recovered through washing, through scheduled washing of the component. Second types of physical faults that happens in gas turbine is erosion. It's a gradual loss of material from the surface. So it affects the surface roughness of the gas turbine, increased tip clearance, change in aerofoil profile, and an increase in air mass flow for turbine and compressor, because erosion has different effects in compressor and turbine. In compressor, it reduces the flow capacity, but in turbine, it increases the flow capacity because it's expansion on the turbine side. So the removal of material will increase the flow capacity. The third one is corrosion. It's an irreversible deterioration of component as a result of oxidation, reaction, or chemical interaction. It can be classified as cold corrosion and hot corrosion. It affects in blade surface roughness, blade profile change, and increase or decrease in air mass flow for turbine, compressor, and it decreases the isentropic efficiency of the component, the turbine and the compressor as well. And the other one is the foreign object damage, when it happens when some foreign objects gets into the gas turbine. For example, if birds or other wildlife, stone, forest, snow, ice, or runway, the foreign particles are entering the gas turbine. That causes blade surface roughness. It increases the blade surface roughness, alters blade profile change, and if the object is big, it can cause crack or break the blades as well. So, these are the most common gas turbine faults. The most dominant one is the fouling, but the rest of erosion, corrosion, blade clearance, domestic object damage, and foreign object damage may also happen. The causes, as I described it in the previous slides, the performance change. If fouling happens in the gas turbine, the flow capacity in the compressor and turbine will reduce, and the central efficiency as well will reduce. Erosion has the same effect as well. But no, in the compressor, the flow capacity will reduce, but in the turbine, it increases the flow capacity. But the efficiency will reduce in both compressor and turbine side. Corrosion, it has the same effect like fouling. Blade clearance, same. Okay. The next one is types of faults. In gas turbine, we have different types of faults. I mean, the behavior of the faults. Some faults are abrupt faults, some faults are rapid faults, and some faults are gradual faults. The abrupt one is it happens instantaneously, but do not grow in magnitude over time. So it's easier, faster to detect. For example, foreign object damage. If foreign object gets into the gas turbine, it's easily detectable. Rapid faults, the faults that initiate and grow in magnitude over time. Example, the fouling, erosion, corrosion, and sensor drift. You know, it will progress. In the fouling, gradually its effect will be increasing. The gradual faults, slow deterioration of equipment due to natural wear. This one also triggered by fouling, erosion, corrosion, thermal stress. It depends on the severity of the fault. So if we have all of these problems in gas turbine, so how do we tackle this problem? How do we offset when we have a performance deterioration in the system? So we need a condition monitoring tool, a diagnostics tool. And how do you develop that condition monitoring, the diagnostics tool? What are the procedures? So the first thing is data acquisition, the collecting of the data, the event data, the performance data. And second stage is processing the data. And the third stage is developing the diagnostics model, which is condition monitoring strategies. So it has three packages. The first one is detection, second one is isolation, and the third one is fault identification. The first one is the detection module is to detect whether there is fault or not. If fault is happening or not. So it's responsible only to detect if there is fault or not. But the second package is if there is a fault, if the first package detect that there's a fault, second package is to isolate the fault. Okay, if fault is happening, what kind of fault is happening in the system and which component is affected? So it's isolating the type of fault and isolating the type of component that's affected by the fault. And the third one is the identification, which means, okay, fault is happening. For example, fault is happened in the system. Let's say fouling happened in the system, and how much the flow capacity is reduced, how much the efficiency is reduced. So it's quantifying the magnitude of the fault. Yeah, so this one is what I have discussed. We have three modules in fault diagnostic. The first one is fault detection, the task of detecting an abnormal behavior at the earliest possible, which may gradually lead to failure. Second one is fault isolation, the task of determining the type and location of the fault. And the third one is fault identification, the task of estimating the magnitude of the fault. So we have two approaches of developing a diagnostics model. The first one is the model-based. In gas turbine, we call it 1D performance model. You know, just calculating of the gas turbine performance at each stage: a compressor exit, turbine exit, compression chamber exit. So we have a baseline. When it deviates from that baseline, that means there is a fault. So that's model-based. It uses the thermodynamic equations. But the second one is the data-driven based, you know, which is nowadays widely used. We just collect the data from the gas turbine, the history, the operational data, the behavior, the event. Then we use that data to develop the diagnostics model. So we have artificial neural network, deep learning, fuzzy logic, support vector machine, decision tree, and so on. So generally, we have two approaches. Performance-based, we have two approaches, data-driven based and model-based. So we'll be focusing on the data-driven approach. because it has several benefits over the model-based approach. So it's more flexible, and it has the capacity of handling noise and bias. And computationally, it's not that much expensive as well than model-based. So we have two types of supervised and unsupervised learning, machine learning. The supervised one is classification and regression problem, and the unsupervised one is the clustering problem. The supervised one, we need to have the labeled data, the inputs and the outputs, to train the model, the diagnostic model. But unsupervised, we don't need to have the labeled data. The system by itself will figure out when we give the input, it will predict the output by itself. So it's clustering. Okay. If we are developing a diagnostics model, I mean, to monitor the health status of the gas turbine, the first stage is, okay. So we have to choose the case engine, the type of case engine. So in this case, we have three-shaft gas turbine. It has two compressor and three turbines: low pressure compressor, high pressure compressor, high pressure turbine, low pressure turbine, and power turbine. That's three-shaft gas turbine. But we have different types of gas turbine. We have single shaft gas turbine and double shaft gas turbine. So when someone is planning to develop a diagnostic model for a gas turbine, the first thing what he has to do is literature review. He has to collect the data. Yeah, and he has to collect the data if he's planning to use the data-driven techniques. You need to have the engine information. Maybe you need to collect from the data from the engine manufacturer or from the operation side. Then nowadays, getting the data from the actual site is very difficult, and it's very expensive. So what people do, they develop the gas turbine performance model. They get some small amount of data, for example, the engine manufacturer information. Then they use that data to develop the engine performance model. Once they validate the model with the engine manufacturer data, then they will use that model to simulate faults and generate a data that will be used for diagnostic development. That's the current approach. It's cost-wise and many other factors. So the first thing we need to do, data collection, then developing the gas turbine performance model. Then once we validated the gas turbine performance model, we use that model to generate both clean and faulty data for diagnostics model development. So, for example, in this case, this is the engine information. The design point information of this for shaft gas turbine, and the graph shows the variable electric advance scheduling of the gas turbine. So once we develop the model, we need to validate the model like this. Here it presented the design point performance model validation, the data sheet and the model and the discrepancy, the error. And the graph shows the entire operating range of the gas turbine when the model is validated within the entire operating domain. So let's say now the model is validated with the engine manufacturer data. And the second stage is to generate faulty data and clean data. So how do you do that? So if we plan to develop a diagnostics model that detects the compressor and turbine fouling and erosion, so how do you simulate fouling in using the performance model? How do you simulate erosion using the performance model? So this is the approach. This is the relation between the flow capacity and the centropic efficiency. So this is experimentally validated approach. So to simulate compressor fouling, we need to reduce the flow capacity by 7.5 and the eccentropic efficiency by 2.5. So the ratio is 3:1. 3:1. And the same approach goes to compressor erosion as well. If we simulate erosion in the compressor, we need to reduce the flow capacity by 0.4, by -4, and the eccentropic efficiency by 2%. So the ratio is 2:1. It goes in this way when we simulate faults using performance model to generate a full set of data that will be used to develop the diagnostics model. So this is how we simulate the fault and to generate faulty data using the performance model. So we have selected diagnostic measurement parameters. This one also suggested by conducting the correlation and sensitivity analysis. Specifically for three-shaft gas turbine, we have 10 measurements that will be used for diagnostics development. So now we generate the input data for diagnostics development from the performance model. But in the actual operation, in the field, in the site, when the data is collected using sensor, there is sensor noise. So we need to account that noise level in the data that's generated from the performance model to represent the actual scenario in the field. So we need to add, for example, for temperature, up to 0.4% standard deviation, or pressure, 0.5% standard deviation, fuel flow rates, 0.5, and shaft speed around 0.05%. So this noise level has to be incorporated in the data to represent the actual scenario in the field. So we'll have a labeled data. For description, for example, for low pressure compressor, LPC means low pressure compressor. Fouling, HPC fouling, HPT. These are the components of the gas turbine. And for the ID class and observation is the data, the number of samples. And we make sure that the data has to be balanced. For example, the clean and the faulty data has to be balanced for each component as well. So as you can see here, 336 for each faulty descriptions. So once we have the labeled data, the next stage is to just train the machine learning model. For example, here, just to show, I presented the neural network approach. So load the data. The first thing is just generate the data, then add noise label, then data filtering, then normalization, then after that feeding into the neural network model, data partition, 70%, 75%, and 25% for training and validation, dancing data. And then the rest is just tuning the model by changing the number of neurons, changing the activation function. So it's going to be just try and error by seeing the performance of the model. So the first one is, right. So this one is the label data just to detect and isolate the faults, so fault detection and isolation. And the second module is the fault identification. The fault identification is, we have performance indicator parameters, the flow capacity and the eccentropic efficiency. So the predictor is to predict the performance indicators, the flow capacity and the eccentropic efficiency. Those two parameters are the performance indicator parameters in gas turbine, the flow capacity and the eccentropic efficiency. The predictor is station parameters at each station. That's Low pressure compressor, exit, high pressure compressor, exit, combustion chamber, exit, high pressure turbine, low pressure turbine, and power turbine exits. So this one is fault identification model development flowcharts. The first stage is same with the fault detection and isolation approach. I mean, the sequence is the same. Load the data, noise addition, data filtering, normalization, and data partition training 70%, validation 15%, and testing and dancing 15%. Then feed into the model, and then choose the training algorithm. In this case, most of the time we use the Levenberg quadrat backpropagation algorithm because it gives more promising result. So once we train the model, then how do you evaluate its performance? So the confusion matrix comes here. We have true positive, true negative, false negative, false positive. So A is number of corrected detected fault patterns, that's true positive. False negative means number of fault patterns wrongly detected as no fault. False positive means number of no fault patterns wrongly detected as fault. And true negative is number of correctly detected no fault patterns. So when A plus B, total number of faults, A plus C, total number of alarms, B plus D, total number of non-alarm, and C plus D, number of no fault pattern. And when we add up A, B, C, D, total number of test patterns. So the final accuracy, the accuracy of the model will be calculating true positive plus true negative divided by the summation of the entire true positive plus false negative plus false positive plus true negative. And to make it in percentage, multiply by 100. That gives the accuracy of the model. So how do you say when the model is robust? Robust, I mean, how do we be confident on the developed diagnostics model? So what are the requirements? And the first one is if the model had the ability to deal with system non-linearity, a trade-off between linear model assumption, diagnostic problem. The second one is the ability to cope with sensor noise and low development implementation cost, and computationally shouldn't be expensive. So I will leave the presentation by just showing some examples, the case engine. So the first thing is to describe the problem. I mean, selecting the type of the gas turbine. In our case, we work on 3-shaft gas turbine. So the gas turbine that has 2 compressors and 3 turbines. And then having the data, the history, I mean, the event that represents the gas turbine. We need to have the labeled data for each fault scenarios. Labeled data, and the data has to be balanced as well. So let's say this one, the data, the input data for each 10 parameters. Then the next stage is filtering. It's a part of data processing. We have to filter the data to remove some outliers. So we have several types of filtering techniques. One of them is moving average filter. It's like, it works like if we add up the first 5 data and divide by 5, taking that average as input, and the next one as well. So it works in that way. So this one is after applying moving average filter to denoise the data with the frame length is 10. So the frame length is like here, for example, L. If L is 4, so that's the frame length. So the blue one shows the data that's not filtered, and the red one is the filtered data. So this one, then after training the model, the diagnostics model, finally this is how we see the accuracy of the model. So the true positive, true negative, false positive, false negative. And finally, at the end, if you see here down at the right corner down there, that's the accuracy of the model. The overall accuracy of the model is around 96.6%. Yeah. Yeah, that leads me to end my presentation. And if you have a question, that I'll be very happy to respond.
मैम डायरेक्ट बात कर सकते हैं आप? Yes.
Thank you so much, sir, for the valuable insights. And I request of all the participants, if you have any questions, interactions, we have the time right now.
Hello, sir. Am I audible?
Yeah, I can hear you. Let's go ahead.
Sir, can we adopt AI and ML in predictive maintenance through condition monitoring?
Machine learning. Yeah. Those techniques, the data-driven techniques, are machine learning techniques. So we use them. My experience tells me that, especially for Gastarbarian, neural network is found to be the most promising technique. Yeah, but these days, new tools are coming out. So reinforcement learning, transfer learning, some other new techniques coming out. So you may also use the new one. Did I address your question very well?
Any other questions?
Hello.
How does condition monitoring help prevent unexpected equipment failure?
Hello, sir.
Yeah. Go ahead.
Sir, how does condition monitoring help prevent unexpected equipment failure, sir?
Yeah. Because the condition monitoring means it's just by assessing the performance of the system. So you know how the progress of the fault is going. So every time, if I use the station parameters for the condition monitoring model development, so if there's a deviation from the baseline, so you know something wrong is going on in the system. So then your second task might be just taking maintenance action.
Hello, sir.
Yeah, I can hear you.
Sir, I have a very basic doubt regarding the activation function that you selected was ReLU, I guess. So, in the hyperparameterization tuning, is there any reason for selecting or going for the ReLU function, or rather, how to select that hyperparameterization tuning, or how to select the activation function, especially for the condition monitoring? I mean, did you went brute force method, or is there any math behind?
Okay, that's a very good question. You just try and error, actually. Maybe you try with ReLU, then you see the performance of the diagnostic model, and you try with other activation functions, and you see. If you're asking me my experience, ReLU is the most promising activation function when it comes to Gastarbarian diagnostic model development. But I just figured out that one by just try and draw. Just change the activation function and change the model, and you see the prediction accuracy, and then you change as well. So I cannot give you any comprehensive rule to select an activation function. You just try and drag.
Okay. Thank you, sir.
Yeah, you're welcome.
Yeah, Mr. Gajanan, sir, you can ask.
Yes, sir. Sir, my question is, we are relying on sensors and IoT devices.
I'm sorry. Can you come again?
We are relying nowadays. We are rely on IoT and sensors for maintenance.
Yeah.
So, how much it is centralized? Because is there any necessity of decentralization? Being a human as a one component, again to monitor that sensor and all.
In diagnostics, we have two problems actually. The one is, the fault comes from two parts. One is from the component, and the other is coming from the sensor itself. So the sensor deviation, each sensor has to be monitored independently.
So decentralization is necessary again in that case.
Yeah.
Yes.
Yeah. So you treat each sensors independently.
Decentralization means human interfere is again necessary, or it is not required at all.
No, it's necessary.
It's not necessary.
No, it's necessary.
Yes,
Yeah.
yes. I got it. Thank you.
Yeah. All right.
For the valuable insights and for the interactions. We hope we have future interactions ahead as well. Thank you so much. All the participants.
Thank you.
Yes, all the participants can move for lunch, and I would request Roshan sir, if you would give some.
No, I'm not getting anything now.
Yeah. Hello.
Hello. Yeah, I can hear you, Dr. Roshan.
So, on behalf of organizing committee of ASSET 2026, I extend my heartfelt gratitude to you and all the participants for making this session success. Thank you.
Thank you very much for inviting me in this conference. I really appreciate it, and I appreciate the audience for the interaction as well. It was very engaging. Yeah. So thank you.
See you. Thank you.
All right. Bye bye.
We can leave now. Thank you.
All right. Bye bye.
Bye bye.
Bye.